So I'm recording from now on. So we're continuing today with Anova. So there was a mix-up with Practice Lab 3. I didn't post Practice Lab 3. So I have now remedied that mistake. I've sent an announcement with Practice Lab 3 with the code. So please use this code and then just resubmit. And those that haven't submitted yet, please submit it. It was due already. So that was a mix-up from my end. Just work on that. I will post a video explaining Practice Lab 3 and also Practice Lab 4. I'm not sure how much of Practice Lab 4 we will be able to get to today. Again, I reiterate what I said about the practice labs. This is 3 points, so to say. It's just something that you really should run, that you have an exposure to R. It's not something I will grade hardly or strictly. It's just the idea behind it is that you will be exposed to some extent with some statistical software, and it will be an advantage for you if you have some exposure. Well, Amira was first, yes.
Yeah, so practice lab 3 is already due, so if you resubmit the R code,
yes, just resubmit it, run it, and then resubmit it. It's fun. Yes, no, they're fun.
Wait, what if you already graded our practice lab 3? What if you already graded it?
It's what? Sorry?
What if you already graded it?
That's fine. That's fine. It's the maximum. It's either 0 or 10. So you get the 10 points. Just resubmit it. I will just put like the one submission and then give it a look. Have a look at it. As said, 3 points, right? So this is just really something which I want you to save. That down the road you're gonna have it at your disposition. Yes, Ian.
Oh, so because you said that solution. And you said that there was practice lab 3 solution.
Yes, the solution is just run this in R and then send me the text file, and that's going to be sufficient. All right. Thank you. No, it would be an illusion to ask from you that you learn coding within one class. This is not happening, and I'm well aware. It's just I think it's good to have a basic library of code started. That's the idea. Practice Lab 4 also has posted. I posted this earlier. So this is what we're gonna be discussing and practicing today. So we're gonna talk briefly about the one way between groups Anova again, and then we're gonna focus on the one way within groups Anova, which is a modification. It's a slight modification. It's not substantially different from the between groups Anova. Quiz 2 on Wednesday is going to be only t-distribution, no Anova. So, but the Anova will be part of the finals. Again, of note, I posted 3 slide decks between groups and one way between, one way within, and 2-way between groups Anova. There will only be the one-way Anovas on the finals. The 2-way, we're not getting to it. I just posted this that you have it at your disposition. Good. Any questions? And then next week we're gonna be talking about linear regression, and we're gonna have a lab day. And the lab day is really ask your questions, ask the questions you have about Excel, R. Let's just talk through things. Also, I talked to Evie before. So if there's some appetite from your end that we're gonna do a Zoom session on how to use Excel, how to use R, I'd be happy to accommodate that and go on a 1-2 hour Zoom call where I walk you through the basics of Excel and R. I'd gladly do that. I think it's just, you will see how useful Excel is once you're actually exposed to it in the real world. And Excel is really something, it's the basic of most jobs. You will get exposure to Excel for sure. And I like the software per se, and I'm happy to help you to get a little bit more insight, a little bit more skills in Excel. So just let me know if there's some appetite. I'd be happy to do that. We just need to find a timing then that works for all of us. That would probably best. So I can send out a doodle. I don't know. Do you have a reading week, right? Would that be a good timing for something like that? You're supposed to be reading, but you might as well help on Zoom. I don't know, is that an option? You're quite flexible there. And I'm also not teaching during that time, so that makes it easier for me to, so that we use this time like on a Monday evening, and we reserve like 2 hours, and we talk through Excel and R. Yeah. No, it wouldn't be a class. It would be an additional class that I'm offering for you guys to just get a head start.
We don't have other classes, so like.
All right. Well, it's voluntary, so it's really just something I'm offering to help you get forward with that. Yes, I would record it. No problem. Okay, so this is this. And if there are any questions, just really let me know. I really want to help you as good as I can. So review of Anova. It's actually another review because it's we didn't get to the one-way within group Anova, so it's basically we're focusing on that, and then we're reviewing those classes to some extent. Also, when you look at the practice labs, and that's just a quick walkthrough, a quick idea. So essentially you have on the R code, you always have like the removal of all objects in the environment. You have the building of data frames, which Evie pointed out to me that this didn't work in the posted version. So this here works. And you can run this, and this basically recreates that data frame, this object that you can run analysis on. And these are just the same codes that you essentially know already from Excel. It's nothing else, and it gives you the same value. It gives you, with one touch of a button, it basically gives you all these parameters that you need, or the statistics that you need. And it answers all the questions like in a sequential manner. And with the t-tests, with the t-test function, you actually get all the results as we have calculated them in class. And you will see, please play around a bit with it, and I will post this video and explain it a little bit more in detail, what I did and what it's for. Same with practice lab 4. You have with practice lab 4, you have essentially the same principle. You just need 2 additional packages that I'm installing right now on my Mac, which was actually not that good. So these are packages that essentially allow you to approach this data in the manner that you need them for the Anova. You get the 2 data frames in your environment, and you're grouping them then here in a certain format. So this is a grouping code that essentially can be helpful. I don't know, those of you that are more inclined in computer science and data science will know in approximate terms what that means. I will explain it. It's basically, it's a summarization of all those computations that we have computed in Excel. And these summarizations help you then to essentially get those values that you need for the further calculations. And I will explain and elaborate on that on the video. So with the Anova, you build here the source table just in the same way and format which we did in Excel. And this is what I meant, is like all statistical softwares essentially will give you exactly this Anova table. So this what we calculated laboriously in Excel, you basically get was at the touch of one button in R automatically computed with the same values as we have computed them. This is true for the between group Anova as well as for the within group Anova. And then here, there's the Taki honest significant difference test, which we have discussed, which essentially calculates you a Q and allows you to compare the pairwise groupings against each other and evaluate all these differences between the groups. Here for the within group Anova, it also gives you a pairwise t-test, which essentially is using the Bonferroni adjustment. If you recall, the Bonferroni adjustment is where basically you divide your critical value, the p-value that is considered your critical value, by the number of comparisons to minimize the risk of a type 1 error. Any questions to that? I will talk about this more on the video. So what do you remember from the one-way between groups Anova? Why is it done? What is the advantage of an Anova? Yes.
The thing with alpha,
It decreases the actual type 1 error, yes. So the problem that you have when you do several comparisons is that you will run into an inflated type 1 error. And this is really an exponential increase that you will see differences that you shouldn't have seen, which essentially are not existent, which can be just due to random error and random chance. So for that very reason, you use an Anova, and I really reflect this slide. This is a very nice slide, basically showing that essentially shows when to use which test. So you essentially do, in the knowledge of the mu and the sigma from the population, you will employ a SAT test, and you basically can then use, under the assumption of a normal distribution, you can use a SAT statistics. When you have to calculate the standard deviation and estimate the standard deviation of the population based on the standard deviation of the sample, you will resort to a t-distribution. With a one sample, where you have one sample comparing it to a population mean, you will use a one sample t-test. If you have two samples, you pay attention, what are you comparing? Are you comparing two independent groups? Then you will use an independent sample t-test. Are you comparing within one group a before and after condition, or something that is chronologically distinguished from each other? Then you will use a paired sample t-test. If you have a continuous variable analyzed as a function of a nominal variable, and you have three or more groupings, then you will go towards an Anova, because then you're inflating your type 1 error by multiple comparisons. And the good example that they provided here was here the likelihood of a car crash when you're A, drive alone, B, with a passenger that you may have a conversation with, C, with a video phone condition, or D, was a cell phone condition where you're actually on the phone. And this is a good example, essentially, where you do comparisons within several groups. And this would be a classic example of a between group comparison. You could also do it as a within group comparison, and this is what we will talk about today, where you have the likelihood of a coalition within the same individuals in 4 different conditions. Then you would use a within group Anova. And this is going to be on the menu today. So what you essentially do, you quantify the variance between the groups, and you divide it by the variance within the groups. By that, you get the so-called F score. And this F score is the score that you're testing against an F distribution, which is a unimodal right-skewed distribution with a critical value that is determined from your F-score table, where you can say with a certain threshold that you will reject the null hypothesis, which essentially is that there is no difference between the groups. When you have a significant F value that is exceeding that critical value, you can make the assumption that one of these means in your groups are significantly different from the grand mean. And this example essentially is nicely illustrated here. So this is the cutoff. It's nicely illustrated here with the example of the dictator game that we discussed last time with the between groups Anova, where basically you have this grand mean and you're comparing each individual groups to this grand mean. And if one of these significantly differs, you get a significant F score. And by that, you know that you can do further testing, which we did. So you compute the F table, the source table, where you basically have the sum of squares, the degrees of freedom that you quantified for the groups, for the within groupings, and in total. You get these mean squared, the standard error of the means for each of these groups, and by division of those, you get to the F score. So this was the example we calculated. You get to the F score table, which was done last time. You get to a decision you reject your null hypothesis, and then you come to an effect size, which is calculated in the same fashion as for, okay, with the regression, we're going to come to the same calculation. So it's basically the sum of squares between divided by the sum of square totals. So it's the proportion of explained variability by the total variability. And it's basically, it's the effect size of how insightful your Anova essentially is. You have, again, you have conventions, just like with the effect sizes that you have calculated for the T statistics. You have small is 0.01 to 0.06, medium 0.06 to 0.14, and everything greater than 0.14 is essentially large. Of note, this R square is only ranging from 0 to 1. So that's why the convention is a little stricter than it used to be for the T distribution. When you have a significant F, you will do post hoc testing, and only that will lead you to post hoc testing. If you do a post hoc testing without it, then it would have needed to be a predefined interest in a group comparison. Then you can do post hoc testing as well, but it's always important to keep in mind the risk for a type 1 error. So these are the a priori bland comparisons. So a priori means it's before the thinking. So you basically you do the thinking before you actually do the test, which is essentially pre-hoc, ad hoc, and post-hoc. Means also event. Event in that context is hoc. Means if you do it before the event of the test, you do pre-hoc. If you do it at the test, it's ad hoc. If you do it after, it's post-hoc. This is what this post-hoc testing refers to. With a priori is where you do the thinking before, and when you do a posteriori, then you do it after you test it. So this comes from philosophy essentially.
Shouldn't you always be thinking? What do you mean by thinking?
So you basically define beforehand, you think beforehand what your hypothesis you're going to be testing. So you plan them beforehand. So you said before you actually started planning your analysis and conducting your analysis, you already had in mind, okay, I want to compare this group versus this group. And you came already to the stage of the analysis with the preconceived idea that you will do this comparison, irrespective of whether it was significant or not. Whereas a posteriori or a post hoc, you would be driven by a significant difference.
So a priori is saying this is what I want to test, and how does the data show that? And then post is saying this is what the data says, so that's how this connects.
Exactly.
I see.
So this is tachyonist significant difference test. This is where you calculate the Q and you compare the groups with a Q test, where you have your own separate table, essentially reading the Q against. But the most common one essentially is the Bonferroni test, which is a post hoc Bonferroni adjustment, where basically you divide your P level by the number of comparisons. And by that you get a different alpha. And so this alpha level here differs with each comparison. So as you have seen, the increase of the type 1 error being exponentially increasing, here the p-value and this threshold is exponentially decreasing, and that's how you counteract the increasing risk of a type 1 error. That's the idea. Any questions to the between group Anova? If not, yes, questions? No specific questions. So if there are questions, always use the discussion board, and I'm happy to also try to find some time and accommodate your questions in a video or something, or in emails or an additional session. Good. So this being said about the between group Anova, and now we're basically moving forward to the within group Anova, and the within group Anova essentially does in principle the same. It just takes an additional dimension into account, which is the subject per se. So now you have 3 degrees of freedom you're dealing with. You have the between groups degree of freedom, You have the within groups degree of freedom, and you have the subjects degrees of freedom. And the way this looks like, we'll see now. So it's basically, it's like a paired sample t-test. You have a chronological order, you have conditions that are distinguished from each other for the same individual. So essentially you do something that is here labeled as a repeated measures Anova, which is kind of the most common nomenclature that you will find. So you have the same participant doing multiple scenarios, multiple conditions. So you have one independent variable with at least 3 levels, a scale-dependent variable. So that's important. You always need a scale-dependent variable. And same participants. So these are not independent from each other, which used to be one of the assumptions of the Anova and one conditions of the Anova. So the advantage of this is that you get a little bit more of a solid estimate because the subject serves his or her own control, right? So you're taking into account that within the subjects, there are same conditions and it has less variability than you have with different groups, because there may be differences between the groups that are kind of driven by the differences in the subjects allocated to each group. This falls away with the within groups Anova because it's the same individual. So going back to the big data game is not a good example, but essentially you would have the same kind of subject doing the same condition, playing the game in the same style of fashion. So now this time we come to, so we did wine rating. So now this time we're doing beer rating. So you have a beer lover with a certain preference for a certain taste in beer who will rate 3 different beers. So obviously the subject per se doesn't change, the subject is the same, and his or her preference will also not change. So his rating will be driven really by the beer rather than his own taste preference. So that's why this is kind of easier, because it introduces less variability in your analysis. So the groups are identical for all relevant variables because each group includes exactly the same participants. It reduces the within groups variability due to differences for the people in the study across groups. This is exactly what I said. It's the same individual. Thus, you have less variability between the groups in individual characteristics of the subject. The calculations are not entirely similar. Well, they're comparable. They're very comparable. You just have to deal with this additional dimension of the subject, which makes it a little tricky, but not too tricky, essentially. And you get, in addition to the within groups and the between groups sum of squares, you also get now a subject sum of squares, which is calculated in addition to that. You also get an MS subject, so you get a standard error on the subject level, and you also get an F-score for the subject level. The subject sum of squares reduces the within groups sum of squares by removing the variability associated with participants' differences across groups. What is to be kept in mind that the sum of squares that you calculated for the subject is not part of the hypothesis testing. It just removes from the overall variability. So it becomes an additional point, but it adds to the total sum of squares, meaning the hypothesis testing per se is again only done for the between group and the within group sum of squares, which we will see in a bit. So steps of hypothesis testing. We're identifying the populations, the distributions, and the assumptions. We state an R and research hypothesis. We determine characteristics, which we do by doing descriptive statistics. We determine critical values and cutoffs, calculate the test statistics, and make a decision. It's the same menu as it was with all hypothesis tests, this time just tailored for the use case of a within group Anova. What is different now, and I just want to go back to the old slide, that you have now a subject, and that you have each subject doing each condition at least once. And as for the, so now I'm going here. Yeah. So this is what we discussed last time. So we have 3 assumptions for an ANOVA. With the most and foremost, most important assumption, it's normally distributed. Particularly when you have small sample sizes, smaller than 30, normal distribution is essential. You have a random selection of samples, which means they're not in any way biased and not in any way chosen to be in either group, which to some extent with the subjects is less of a problem, but it's still an assumption that needs to be met. We have homoscedasticity, meaning that the variability between the groups does not differ beyond a certain amount, which is recommendations differ. The conservative one is it shouldn't differ more than 20%. And in addition to that, for the within groups ANOVA, we have that the order in which the group condition was met by each subject was not in any way systematic. So that there's not an order effect. You remember when we talked about the order effect? Where the order in which you actually meet each of these conditions plays a role in your rating or in your actual outcome, in your scale variable. So, and for beer, I think it's easy to imagine what that could be, right? So when you test the first beer, then maybe the second one or the third beer is actually not that bad anymore. So it's along these lines, it's kind of to be thought about. So basically order does to some extent play a role. For this very reason, and we talked about this with the order effects, you do counterbalancing. That means that you have a washout period between the conditions, where you basically have, like, for the beer example, you have 1 day in between the first tasting, and then you have the next day you have the second tasting, or you randomize in which order each individual starts the beer tasting, or whatever condition it essentially is. So by that, you essentially counterbalance this order effect, and you have individuals start in a random fashion in each of these conditions. It's very common with randomized controlled trials, where you have a crossover design, meaning they start with one condition, they continue in this condition for a certain period of time, and then they switch over to the second group, and they become then a control group subject. And if you have this in a certain order and there's an effect that is carried over, then essentially the randomization is the counterbalancing that you need to essentially avoid an order effect, to change your insights, change your hypothesis testing, and change your test statistics and your analysis. Any questions to that? Is it to some extent logically? Is it good to follow? Okay. Let me know if any questions at that point. So again, you use the F distribution as the comparison distribution. This is a unimodal right skewed distribution, which I have here. Right here. Here's a nice depiction. So again, this is the distribution. Here's the majority. If it exceeds the critical value, you are rejecting your null hypothesis, which is that none of the mu's are different from the grand mean. So you state null and research hypothesis. So again, this mu1 equals mu2 equals mu3. So there's no differences between these means. Whereas the alternative, at least one mu is different from another mu. So, and now let's get started with, no, not yet. Okay, so we determine the characteristics of the comparison distribution. So now we're going to get to the B example. Let's carry this over. Somehow. Okay, so here's now the B example. So we have a degree of freedom between. Okay, so the following example, Nolan and Heitzen present the following examples. So we wanted to know whether recruits could distinguish between widely available American beers. They had high-end beers, mid-range beers, and cheap beers. these beers were rated in terms of their taste by 5 different individuals. They gave it a rating, which I don't know what the scale is, on a scale to 100. And they did that for each category of beer with five participants, which means 3 beers, 5 participants. We are now essentially looking at degree of freedom between of groups minus 1, which is 2, right? So we have 3 groups minus 1 gives us the degree of freedom of the groups. It's 2. Now we have the DF subject. This is the number of participants minus 1. With 5 recruits drinking 3 beers. 5 minus 1 is 4. Now we have DF within. And this is now where we're back to. So now we have the subject meshed in the DF within. So now we're getting, and this you will notice because you remember that between group Anova, essentially we have now an inflated DF within, which is actually more than we had before. So we have DFB between multiplied by DF subject. So this is DF between is 2, DF subject is 4. So now we have 8. So DF within is 8. So each individual counts for the number of conditions, for the degrees of freedom of each condition. So DF total is now the total, which is when you have 5 individuals, 3 beers, it's 15, minus 1 makes it 14, right? So DF total. So as you can see, the degrees of freedom are essentially, to some extent, larger than we had them with the DF, with the between groups Anova. So this already emphasizes that in the design of the Anova, it is accounted for that there's less variability, making the criteria, the thresholds, a little bit more strict. So this being said, you will also notice that the degrees of freedom for total essentially are the sum of between subject and within. So you have 8 plus 4 plus 2 makes it 14. And this is an association, please keep in mind for the next homework, because they will be asked to complete source tables that will require that inside. Good. Back to this. So these are the degrees of freedom. So this is how you this is how you determine the characteristics of your comparison distribution. And now you need to determine critical values. And this you do on the F-score table. And you have numerator and denominator. As you remember, it's between groups variance divided by within groups variance. So the numerator is the between groups variance, or sum of squares, which is 3 groups minus 1 is 2. So for the numerator, we're looking at column 2. For the denominator, for the within groups, we said decrease of freedom of subjects, which is 5 minus 1, multiplied by the degrees of freedom between the groups, which is 2. So that's 8. So now we go in column 2, we go all the way down until we find 8, which is right here, 2, 8. We are interested in a threshold, an alpha of 5%, which is now here our critical value of 4.46. Make sense so far? Yeah. So the critical value here is 4.46. Any questions so far? The F-score table, are you comfortable with the F-score table? It's really, you need to know what is numerator, what is denominator, and then you just have to follow the grid and the columns exactly to that cell that you're interested in. So once again, just to make sure that you know how to read this. Numerator, degrees of freedom between. 3 groups minus 1 is 2, gives you column 2. Degrees of freedom within is subjects, 5 minus 4, 5 minus 1 equals 4, multiplied by degrees of freedom between, which is 2, so it's 8. So we're looking at 2 and 8 at 5%, which is 4.46. Okay. So we determined that. And now we're coming to the calculation of the sum of squares. And there, essentially, you do nothing else. Nothing else than what we have done already with between groups Anova. So we have the sum of square total. This is our individual x minus the grand mean. This is essentially what we are going for this analysis. Then we have the sum of squares, so we're squaring it and we're summing it up. It becomes the sum of squares for total. Then we have sum of squares between, which is the mean of each group minus the grand mean. This is the variation between the groups. We're squaring it, we're summing it. Gets us to the sum of squares. Sum of squares subjects is the mean for each participant. And this is different now, because we need to sample this out. This particular variability for the participant essentially becomes mean of the participants minus the grand mean squared, summed up, becomes sum of square subject. And as you can see in the calculation for the sum of squares within, it's sum of square total minus sum of square between and sum of squares subjects. So this is how you remove the variability of the subjects. And that makes it less variable and a more conservative and more reliable estimate. So let's calculate this. The moment you all have waited for, right? Okay. So we have, so let's arrange this a little more. Okay, so let's move this on the side. And it's basically, it's the same outline than we had last time with the between groups. So we're doing the mid-range peer and this. So we just need to rearrange it. We need to rearrange it in a certain format that essentially is best like this. Now we have cheap beer. These are the first 5 entries. Then we have mid-range beer, second 5 entries, and high-end beer are the last 5 entries. That becomes the column beer quality. Good. Just a note in terms of statistics. This way to the big data is called a wide format. This is a format which in SPSS, if you do analysis in SPSS, you will use wide format actually more frequent than with other softwares. What we did here, we brought wide format into the so-called long format. Long format essentially is characterized by having redundancy, but each row is representative of each cell in the wide format. So by redundancy, you distinguish between each individual entry in the long format. This redundancy is super important, and this many statistical softwares, except for SPSS, will actually require you to bring it in that format. So keep this format and this step, which we've just done, in mind, because this is something in R, for example, you need to program it, and it's kind of laborious to do that, but it's important that you follow the outline of doing that. So essentially you redundantly state the condition you essentially are reflecting with each individual participant's entry. And you basically, with this redundancy, you actually make each entry here unmistakably standing for one characteristic. So you're collapsing the variables and the dimensions down to a smaller number of dimensions, but you're inflating the actual entries in the matrix.
Is there a way to do that? Like with the formula?
In R, yes.
In Excel?
In Excel, you have transpose. You can do a little bit with transpose. I am not aware of really functioning good ways to do that, to be honest.
So I have to like copy that?
The copying is, to the best of my knowledge, the most efficient way. And it's also the way that leads to least confusion. One of the biggest issues is when you do that, this is actually a very dangerous step to do. This is very, very dangerous, because if you lose an oversight, you're mixing up your entire data set. And you may end up with, I don't know, analyzing the water levels in Venice. So it's really, it becomes absolute useless data if you do that step wrongly. So this is a very sensitive step. So what I did now, more like casually, like just copying stuff down, is something which in the real world, you better double check, triple check, quadruple check, quintuple check. It's like, it's very dangerous.
Wait, so why do we do this here? Like, what's the point to spread it out like this?
Well, because we're doing calculations now, right? Everything is about efficiency.
Right.
So I will post a spreadsheet, but this is a little different. So you can actually do it in a different fashion and like keep them separate. But it's easier to do it that way because by that you can just propagate the formulas. You just put them down, right? That makes it a little easier. And to be honest, the between group, the within group Anova is a little bit. No, it's not. Yeah, maybe a little spicy. No, but it's also it's a little complicated to do because you need to do a subject mean, which to your question, Evie, from before, why is R better than Excel? Like, so you have here the participant entries, right? Participant individual entries. In R, this is one line of code. Here, it requires for us to essentially go like one by one by one. So in terms of efficiency, this increases efficiency to make it, to bring it into a long format. And in terms of efficiency, coding this in a more advanced fashion makes it even more efficient. But again, this is down the road. Okay, so we need sum of squares. We need sum of squares total, within, subject, and between. First of all, we always need a grand mean. The grand mean is easily calculated by just calculation of the grand mean, right? So this is average of all these entries. That's simple. So we have here our grand mean. And this is the basis of everything. So essentially, let's go back to this calculation. Let's copy this over. We don't have to go back and forth. So now we are, let's bring it here. Yeah, that's good, huh? Okay. Okay, sum of squares total. Let's start with the simplest. So the simplest here essentially is an individual x minus the grand mean. This is easily done, right? So we have x and what? That's x minus gm squared. So this is now the formula, and this is a little bit. This is a spicier formula. So so we're having parentheses, individual x, individual entry minus $, grand mean. Excel. Okay. So M10 minus M26 here, my spreadsheet. So we are essentially locking in the grand mean because we want to just pull this formula down. So that's why we need to lock this guy in. So we're locking it in, we're closing the parentheses, and then we're squaring it right away in one step. That will allow us to populate all the way down within just one step. So that's, again, it's individual entry minus grand mean squared in one step. I just want to avoid that we do too many columns.
So
Gets
where
confusing.
did the grade mean come from?
This is the average of all these ratings. Wait, this is actually not GP anymore. This is rating now.
How do you? Oh, you do.
Yeah. Everybody on board with this?
No, I don't. Where do you have to lock?
You lock the,
it before the number and
yes, you do it before the letter and then you do it before the number. And you only lock the grand mean, not the X. But this is, so M10 is X. Here my spreadsheet, I don't know where you positioned it. M10 is the X. M26 is the grand mean. I lock it with the dollar sign. I close the parentheses. Please make sure that you have the parentheses locked or closed, not locked. And then square it. Yeah? Good. Yeah? Good. So that's our sum of squares total.
This is kind of like the beginning of the t-test. Remember?
It's the beginning of the standard deviation, yeah.
Yeah, so it's the same beginning step.
And it always is. You look at variability. So variability is quantified around the constant. And the constant here, so the only thing that changes here really is the constant, right? You use an individual entry and you change the constant. You take the grand mean, or you calculate specific means, group means, which we're going to do in the next step, or you calculate participant means, which we do in the third step. Yes?
I'm not getting the same answer.
No?
I'm just going over what you did in
Absolutely.
column.
So first entry in a parentheses minus grand mean, log them with a dollar sign, $2, one before the letter, one before the number. You close it with a parenthesis and then you square it.
Oh, I see. I got it.
Yeah, good. All right, next. Group mean. So we are doing now m minus grand mean squared. What is the first thing we need? The m. And this is where the within groups Anova becomes a little bit painful, because now we need to do equals. You're not gonna like me. Okay. Okay, average parentheses. And you only take the individual entries now from the first group. Average M10 to M14 is just this one group. Okay? We close the parentheses. You have to do this for each group. And this is now where you have to start already here to do the dollar signs.
It's not bad, Ben. Just do it for each one. Same thing.
Okay.
I'm an ecosystem. We do this all the time.
Okay. Good. Average. Okay, we do $M, $10. Oh. I'm really doing lines behind the column. Okay, so average $M, $10 to $M, $14, first group. We're locking it in. So now we need a subtraction after, so we're still within the overall parentheses, right? Now we're subtracting the grand mean from this group mean. And we again have to lock it. And this is now, this is, yes, this is also locked. And now you need two parentheses. No, only one, sorry. Okay, once again, that's completed. Okay. Okay, it's the average of the first group. It's average M10 to M14. You're locking both cells in with a dollar sign. You close the parentheses and you subtract the grand mean, also locked in with the dollar sign. Then you close your parentheses and you square it.
Wait, so why is the mean that we're using only the first group?
Because it's a group mean.
But wouldn't each, like the cheap beer is the first group mean, so then wouldn't mid-range beer be the second group? And I can't know which one.
Yeah, we're only doing that for these 5 entries. And we're doing it for the mid-range beer. We're doing it in a separate step.
Oh,
It becomes 3 steps. For each group, we gotta do the same thing.
okay.
And this is where it's a little bit more painful. And it gets even worse because we need a participant mean as well.
Yeah, I saw this going in a different way, so it's on.
Oh, no, it's, yep.
So what's the answer? Are we not done with that?
What?
Are we done with that first box?
Yeah, are you, yes, you can press enter now, if you're here. This should be the result, 37.82. Yeah? Are you all on Zoom? I can drop the formula on Zoom, if that helps. Because now we only have to pull it down, right? And it's identical for all 5 entries, logically, has to be. So now for the second group, we repeat that procedure, but what we change now is we need a different range. So now we're doing group 2, so we do M15 to M19. Yeah, 19. So now we do M20 to M24. Yeah? Or no? So, and again, if somebody asks about the differences and why R is easier, this is like one line of code. Interesting. Okay. So you have average M20 to M24 for the high-end beer. You have M15 to M19 for the mid-range beer, and you have M10 to M14 for the low-range beer. Yeah? No? Where are you stuck?
I don't know. I'm just getting totally wrong answer.
Is what?
I'm just getting totally wrong answer. Oh,
Ah,
I see why.
Wait, I have to say it.
Oh, this one?
Yeah.
Because we took this column. We just took the beer rating, not the excellence.
okay, again. So I'm also saying something while you're doing this. Okay, so we have the calculation of the total sum of squares, which is individual entry minus the grand mean. Then we have the between between group mean, which is essentially the group mean, group specific mean minus the grand mean. And now we're getting to the participant mean. And this is the really annoying one. So now essentially what we're doing is, everybody kind of there? Yeah?
Yeah.
Yeah, good. I am.
Hi.
Good, I'm glad you're following along. Okay, good. Participant mean. PM minus GM squared. Participant mean minus grand mean. Participant mean minus grand mean. It sounds more complicated than it is. It's not that hard. So we have now, and now you're really not gonna like me anymore. So we have average. Yeah. Okay, let's do that. Where? Okay, zooming in. Okay, zooming in. Enlarging, zooming. Yeah, better? Okay. You're on board with the formula? Yeah?
Yeah.
Good. Participant mean man PM minus GM, participant mean minus grand mean. We are doing average, no, parentheses, average. Individual entry for participant 1, comma. Individual entry participant 2, comma.
Wait, is that 30?
Individual entry for participant 1 was PS3. This is,
You find the average of 300.
yeah, and it's all entries from participant 1. So this is the subject level. So this individual, we're quantifying the variability of this individual tasting all 3 beers, and this is being subtracted from the total mean to get to the within sum of squares. Yes, we will. Oh, actually we won't.
Oh,
No, we won't. And I will show you why.
oh wait,
Not yet.
it's like you're doing it for each one. So if you
Exactly.
log it,
Yeah,
you're
exactly.
only going to get it for the first one.
You got it. Exactly. Yeah. Very good. Very good. Okay, participant mean minus grand mean. What we need to log is the grand mean. So $M, $26. Yeah. Parenthesis closed, squared. Okay. And now,
You drag it to the whole thing or just
no, not yet.
No, just for participant 1.
Just for these 5 guys, here you can do it.
Oh.
And this is how you get, because now the formula has shifted with you. Oh, wow. What did I do? Wait, hold on. Oh, that was actually notes.
Oh. Okay, so now we just do that for. Oh, wow.
No, but there's, yeah,
Wait, wasn't it just for participant 1?
3.
But that was all 3 qualities.
Yeah, make sure you double check. Always double check. A complicated approach like that, always double check. So now you automatically shifted your participant mean downward.
Can you move over to the right a little for a second, please?
Me? But oh, physically, okay.
Thank you.
Get out of the way. Yeah. Should I zoom in? Well, try to zoom in a bit more. Yeah. And now we can do something to circumvent the problem. We would need to do this again. You select these 5 cells. You go in the 6th cell. So you go on, for me, it's P15. You press enter, no, not like this. You just take the last one. No, you take the whole thing. You go Control V. And now here on the right, you see this little sign, paste options. This is where you want to go, because paste options, because right now it shifted your whole formula, right? Your formula is rubbish by now. So you basically go on paste options and you go on values only. Because now you get the same. So you basically, you go on paste options here on the right end. Exactly, it remains the same, but you need the same number of entries. And by that you take the equation out of it.
Wait, what's the difference between pasting it and dragging?
Well, dragging,
It doesn't matter.
dragging is moving.
What do you mean?
Wait, this one is.
Yeah, then you don't make a copy. Well, you can make a copy. So hypothetically, what you also can do, you can select something and you start moving it. So this would be moving, right?
Oh, no.
No. So you can take a cell and like this, you can move it, right? So this, but that would be moving it. So you're moving. So it's gone. So, but what you can do, you press, you can press Option. Huh? Yeah, Option. Yeah. With Option, you're copying it. You drag it, and while you're dragging it, before you release, you press Option. Or in.
No, I understand what you're doing, but I'm asking, like, why would somebody want to drag rather than copy? Like, isn't that the same?
No, sometimes you want to move formula. If you want to move something to a different spot.
Like, if you have to run up, like, the first cell.
Yeah.
And then you drag it down, the formula goes down with the cell.
Yeah, but then it also, then the lower values, they will essentially, they're not locked, right?
Right.
You could lock each of them
Right.
and then drag it. That would work, or move it or copy it. That would work too, but then you need to update them.
Oh, okay.
So you avoid yourself to have to do that
Okay.
by doing paste value only. And now we're doing the same story, but now this time we don't need paste options, we just copy the same thing down. Because now it's only the values. This is only values. The big problem you have is this. Doesn't play a role for our example, but here it's being rounded. And it's rounded, I think it's the 12th decimal, they're rounding. Doesn't make a difference for us now. In the greater picture, it may make a difference. And it's usually another pretty one. So it's to be kept in mind. Good. So sum of squares. What do we need to do to build the sum? We're summing it up. So we're summing the total sum of squares and the between group of sum of squares and the participant mean sum of squares. That's it. We're done. Now we. You just sum it up. You sum from the first entry, first deviation, squared deviation, down to the last one.
You're just doing the sum for all.
Yep, you're summing this. This is sum of squares between. This is sum of squares participant or subject. And now we want sum of squares within. This is now the difference between this is this minus this minus this. And we're done. Now we just need to populate our source table.
Are you summing all the subjects or just like 5?
No, you sum, no, the whole thing.
No, say for the last column, yeah.
Also this, you sum the whole thing.
You know, it's like the same thing repeated 3 times.
Yep. You sum the whole thing because you need these degrees of freedom. You need the entries.
What was the within one?
The what?
What did you sum for the within one?
This is total minus between minus subject. This is this here. So last but certainly not least, we're getting started now with the source table. Yeah, we can actually do this already. Okay, so now we have between, within, subject, and total. As we remember from last time, so this is how this looks like, the source table. We have sum of squares, degrees of freedom, MS and F. Now with the sum of squares, degrees of freedom, MS, and here's the actual F. So now we have between, within, subject, total. Degrees of freedom between is 2, within is 8, subject is 4, total is 2, 8, and 4 is 14. MS is sum of squares divided by the degrees of freedom. Sum of squares divided by degrees of freedom. Sum of squares divided by degrees of freedom. And for the F, we get an F between divided by within. And we get a second one divided by within. Done. So we're doing, it's always the same principle, right? So you get 3 MS entries. You can also do a 4th one, right? You could also divide this by this, should actually also add up. Then you need 2 Fs. You need an F for the overall, between, over, within. Then you need an F subject over within. But hypothesis testing is only done on those 14, on that one. And now we go back to our critical value, which we remember to be 4.46, somewhere here. 4.46, 14.77 is greater than 4.46. So we are rejecting our null hypothesis. And we know now, what do we know now? What's the insight?
I just have a question.
Okay.
What's the F subject? What's the formula for that?
It's the same story. It's a subject divided by within. In the denominator, you always have within. The numerator changes. You have between divided by within becomes the F, the over F, the F between. And the F subject becomes some MS subject divided by MF within. So the denominator is always within. So the conclusion of this is now that at least one of these ratings is different. And well, if we know, if you look here at the, means, let's just do the means for the sake of argument. Let's just compare the mean entries because that's also one thing that you can do, right? Averages. This is the descriptive statistics without hypothesis testing. What am I doing? Without the hypothesis testing, you just look at the differences, and you clearly see that there's a difference, right? Not surprising. So what do we know from that? It's not very surprising. So we know that Samuel Adams is better than Budweiser. Those of you that are allowed to drink beer will know what I'm talking about. So, all right. So we have this. Okay. Any questions? It's a little, it's
a lot. Yeah.
I know it's not trivial, but I promise you one thing, whenever you're going to do an Anova down the road, you will look at it with different eyes now. Trust me on that. Okay. So, but it is clear, right? It's not terribly difficult. It's just laborious to compute, right?
It's not hard. You just need to know the steps.
Yep. Okay. Good. So this was this. So we have 5 more minutes. In 5 minutes, I will not be able to do much. So we make a decision. We do an R square. R square is easy. We do just in the same fashion. No, not this one. We do sum of squares between divided by sum of square total minus subtract. So that's the R square. R square equals sum of squares between divided by sum.
Yeah.
So sum of squares total minus subtract.
Would you mind just moving that to the one in the middle of the projector?
Hmm?
The corner. Right.
No,
Not you.
it's a screen.
That's green.
No.
That's green.
Like, no, just like,
like this will like
What am I moving? The Excel. Okay, that corner.
There you go.
Yes? Okay, good.
Even more up, just like you scroll sideways. Yeah, that
Okay,
works.
that works.
Okay.
Okay. Okay. Enough of this. Total minus subject. Total minus subject. So we have an R square of 1.0. No, that can be. No, there's something else. Second. SS between divided by total minus.
I got a different answer.
Yeah.
Oh.
No, that was something else. This divided by total minus subtract. Yeah. Yeah. Okay. And now, just briefly talking about it, let's look at the same in R with 2 more minutes. So we have now essentially the same analyses. We're grouping this down. We get these groups, exactly the same groups. It's one line of code. Well, it's presented in several lines, but it is one line of code. You get the same analysis than we did last time. You get it with one line of code. What we just did, we're getting here. And this is the beauty of R. This is really the beauty. You can do Anovas very.
Oh, it's beautiful.
I love the spirit. Good. Good. So we have this essentially done, and now we can do pairwise t-testing. since we found a significant difference, we can now pairwise t-testing, and this is the Bonferroni. So now we have to confirm our thinking that Sam Adams is a better beer than Budweiser, which is, yeah, quite obvious. So we have cheap versus high end is here significant with a p-value of 6%. So you got to look at this. You got to imagine this as like a grid. So you go cheap versus high end. This is your p-value. The Bonferroni adjusted p-value. This is mid-range versus high end. So actually the cheap beer is not even that terrible. We know, as a conclusion, we know Budweiser is not as good as Sam Adams. Good. It's not my example. I don't drink beer. Good. Any questions?
Yeah, what's on the quiz?
This is not on the quiz.
So it's 9, 10, and 11?
It is 9, 10, and 11. If this is the T statistics, yes. Yes, 9, 10, 11. Sounds about right, yeah.
So no one knows that.
No, it's one sample t-test, independent sample t-test, and the peer sample t-test. These three will be on the test.
So it's not just multiple choice? It's not just multiple choice?
It's not what, sorry?
No, it is. It is. Well, some of it is.
Okay, good.
It's like all the other quizzes and the midterm, right?
It's the
Whereas
same
like you
story.
do the practice test and then have them
You do the practice tests, you can do those practice. And the next two sessions, I think you're gonna like correlation and regression. These are really fun.
Can't wait.
I like the spirit. Thank you. All right, good. Have a nice evening. See you on Wednesday.
Thank you. Have a good night.
Thank you. Good night. What's that?
Can I send in a third practice lab
Yeah.
I can do that after.
Okay. Okay, sounds good.
Just so you know.